What is a system? So what we can call as system response. Okay, so here is an example. So this is what we have on the input, and this is what we get on the output. Okay, so a system response, we're going to have our system. Let's say, for example, these are the frequency one we get on the input. Okay, so when the signal is gonna go into the system, it's gonna come out in this form, so we can identify the outputs of the system. Okay, maybe let's take this other example, frequency 2. We take the excitation and then we insert it into our system, and then the signal that we get on the output. Okay, so we're going to get the system response. Okay, so we'll be able to define what category we have of a system response. So now what you see here, just a general here. So on a system we have a input, output, and process. So the process is our system. Okay, and when you only have one system, you can write it like this. So if you have multiple system, so multiple process. When you have multiple process, so it's gonna be, you're still gonna have an input and output. Okay, so we need to compare the response that we get from the input to the output, and based on our system behavior. Okay, so now let's see what we have this side. So what we have here, it's the first order system. Okay, so this is how we can represent our first order system. Okay, and for the second order, this is how we can represent it. Okay, and the form inside just to give you the transfer function GS that you see there. So this also is our GS transfer function. Okay, so we're going to see further on what is actually happening inside this process. Okay, and pay attention that for you to solve, you're gonna need to define your term. Okay, depending on your transfer function equation. And also pay attention to this structure. Okay, so let's see in details the formulas that we can use for the first order transfer function. Let's say this is our transfer function. I'm going to zoom in. So this is actually our transfer function. Okay, we have the formula that we can use to calculate for the steady state value. It's gonna be A over B. It's gonna be B over A. Okay, and times it's gonna be 1 over A. So it's gonna be 1 over A. So you can see we have A there. And for rising time, it's gonna be 2.2 over A. Okay, you will see this into the graph that I'm going to show you. So these are the formula that you use. For setting time, it's 4 over A. That's what you're going to place here and solve. Okay, so this is just giving you a range of which value you can get. Okay, based on this system. Okay, and for the second order, okay, this is the second order. This is the form that you get for your transfer function. Okay, so the output over the input in S domain. So this is actually your transfer function. Okay, and K, it's called steady state gain. Okay, damping ratio, this one, this is why we call it damping ratio. And depth natural, it's actually this one that you see. It's repeated everywhere. So we're going to use this form to solve for this one is the damped natural frequency. Okay, and this one you're going to calculate based on the using the undamped natural. And here we got our damped resonance. Okay, you also use the same formula and just solve. And this one is actually the repetition of what of the formula that we're going to need. So for second order, so you can use this one for natural frequency, as you can see here. So it's actually this formula. You can use this one to solve for the peak time, and this one for the rising time. You can use this formula for the sinking time and maximum overshoot. You can use this formula. And remember, all the unknown, you're going just to get them from that equation. So now this, it's based on the graph. Okay, so let me now move to the page where you can see all this information. Okay, so what is happening here? Okay, so you can see this is overdamped. It's when we have the damping ratio. Okay, inferior to 1. Okay, and the example for the overdamped is this one. Okay, this graph that you see here. Okay, and if you want a clear representation of overdamped it's this graph here in case A, where the damping ratio is superior to 1. This is overdamped. Okay, let me just correct my damping ratio superior to 1. Okay, now critical damped, where we have this it's when the damping ratio equal to 1. So where's the critical? Where the damping ratio equal to 1, you can see when the pole representation this side. So you will get this graph, okay, of your system response. Now we go for underdamped. It's when the damping 1 is superior to the damping ratio. Okay, so underdamped, this is underdamped, you will get something like this. So when you calculate, you need to get your value between this range. Okay, it's the same as this side. So for undamped, it's when the damping ratio equal to 0. Your graph is going to be like this for system response. Okay, and for underdamped, it has to be between 0 and 1. Okay, you will get something like this. And for your pole function, your pole is S-plane is gonna be something like this. Okay, I'll show later on how you can get up your pole and how you can calculate the damping ratio with some examples. Okay, this is for the critical damped. You will get the pole like this, and also the system response like this. And here it's overdamped, and here the formula that you can use to solve for. And this is the X-plane. This is what you're gonna get for your overdamped system response. Okay, so this is what we're going to get from the system response, just to know how a system behave. Okay, and we can define this, and we got both pole and then our response. Okay, system response. and then you're going to use, if it's first order, you'll use these formulas here. And then if it's second order, this is for second order. So you can see second order system. I'm gonna use this formula that you see here, or what you see here. It's just something. Okay, this is how you can calculate. And then the main goal is to find the damping ratio. So then you can know how your system is. And even this side. So for second order, we're going to solve for the damping ratio. So for you to know how your system behave, and then you're going just to make this block equal. And if you want to know what is the formula for the damping ratio for the second order, so the damping ratio will be equal to, you take this, it's going to be equal to 2 damping ratio n s. Okay, so you're going to make it equal to what you're going to find here from your equation. After you get your equation, you're going to put an equality there and then solve for the damping ratio. I will show you that later on. Okay, and for the first order, you can only get the time constant, steady state, rising time, setting time. And remember, this is for second order. So all this graph that you see here, it's for second order. Okay, second order. That's when we use, we apply this, okay. Then it's based on the damping ratio. So when we see the damping ratio, we see the second order equation. So for us to know what is the damping ratio, so we're going to work with second order equation to get the damping ratio. Okay, and yeah, this is it, what we just saw. Now we're going to apply these formulas, and then you should be able to get your system response and the pole of your system. And the way we get the pole here, we solve for delta. See in your second order equation, by solve for delta, you should be able to get the pole of your system. I'll show you later on.